I did push back the Mastering Chemistry Introduction assignment to Wednesday because I know some people are still waiting for their book and their code, but I really recommend getting on that. Your homework right now is due after this week, but it's always dependent on how far I get. I'm never going to have your homework due if I don't finish the chapter, but I do expect on being finished with the chapter by then. And I did put up some dynamic study modules on mastering, and this is supposed to be kind of a way, most of them that I put up so far are just some math you should know already before coming in. And I think the way it works, and I haven't used them before, but it asks you a bunch of questions quickly, and once you start getting them right, it's like, okay, you know that, so then it starts giving you something else until you start understanding it. So those don't have a due date. I'm not grading them. They're just there to help you if you feel like you need it. So those, I think you probably have to scroll down all the way. Since they don't have a due date, they won't show up on the calendar. They'll just be on the list because, again, they're just open. And I put an announcement on that. So like I said on Friday, you can set your Moodle to send your announcements, anything I put up to your emails. That way you don't have to always look at Moodle to see that. Okay, so continuing on with chapter 1, the next thing we're going to start talking about, we talked a little bit about density, what that means. We talked a little bit about these measurements and these units we use. The next thing we need to talk about is in general measurements. And what happens when we're looking at measurements in the lab. And how that relates to significant figures. And why significant figures are important when we're talking about measurements. So, the first thing is, what is a measurement? And that's going to be a quantitative observation. And somehow we're using some sort of instrument to quantitatively get a numerical value for something. In this case, it would be volume. And there's a couple of things I don't know about what I'm looking at. For example, I don't know what units this is in. It's likely milliliters, but that's just because I've worked in the lab a while. But it might not be because this is flown up. So I don't know what units this is in. So this one would be volume. It's some sort of graduated cylinder. But we might also be talking about mass. Then we'd be talking about a scale or a balance. We might be talking about other numerical values that we can measure. So either way, whatever numerical values we are talking about, we need to talk about that measurement. So it's a comparison based on an agreed upon standard. And when you do take lab, if you're a chemistry major, you should be in lab now. If you're not a chemistry major, you'll just take your lab next semester. But when you do take lab, you will have a discussion at the beginning of lab about sensitivity of certain instruments. For example, a graduated cylinder is usually pretty well calibrated for volume, but while a beaker has volume measurements on it, usually a beaker isn't used to clearly measure out a volume because it's not very precise. So it gives you an idea of what the volume is, but not quite right. Whereas a graduated cylinder has been calibrated so you can be pretty clear about what you're measuring. So every measurement has a number, and then we have a unit attached, and that unit tells us what the measurement is. For example, if this is milliliters, we know its volume, and we also know about what size a milliliter would be versus a liter. We know a liter is much bigger than a milliliter, so if we're visualizing 1,000 milliliters versus 1,000 liters, we have an idea of the difference in that visualization with volume. And our unit tells us what standard we're comparing our object to. Our number tells us what multiple of the standards is. And the one thing that's important is uncertainty in that measurement, and that's going to come about our significant figures. So we're measuring something quantitatively in the lab. We're pretty certain, let's say this is milliliters, that if our meniscus is here, we're certain we have 4 milliliters, and then this is increments, so this is 4.5 milliliters. But we're not real certain about, we clearly have less than 4.6 and more than 4.5. We might say it's 4.56 milliliters, 4.57 milliliters. Do I know exactly if it's 4.56 or 4.57? No, that last number that I just called out has some uncertainty to it. based on the fact that we don't have any tick marks between this 0.5 and 0.6 value. Now you might have a more sensitive instrument that has the tick marks between that value, and then you can be more clear. We can measure microliters even if it's small by having a microliter instrument to measure that certain amount, but it would be hard with this volumetric, with this graduated cylinder to measure microliters if this is in milliliters, because 1 microliter is a lot smaller than a milliliter. So that uncertainty in using the correct instrumentation for the size of the measurement you want is important. But that uncertainty is also going to be important when we actually report our numbers. If I'm reporting that I measured out 4.57 milliliters, someone who's reading that would understand that that 0.7, that 0.57, that 7 is a little iffy. And that comes about to our significant figures and why they're important. And they're important because of our uncertainty in our measurements, depending on what instrument we're using. And there's some instruments that are going to be more sensitive to measurements, and we need to be understanding of that. So scientific measurements are reported so that every digit written is certain except the last one. The last one is estimated. So for example, if I said this was 4.57 milliliters, I understand that 7 is estimated. It's close. It's not 4.52. That's pretty clear from where my meniscus is, but there's still uncertainty there. And that's why when we talk about our significant figures, and then we talk about adding and multiplying and doing calculations with our significant figures, bless you, it's going to be important to understand why we care about significant figures. And the reason why we care is because of these uncertainties with our measurement types. So for instruments marked with a scale, you determine the last digit by estimating between the marks. If it's even possible, sometimes it might not be very possible to estimate in between the marks. And again, it depends on your instrument and how sensitive it is. So you're mentally dividing the gaps in the tenths and estimating about where it would be, and that's what I did here. This is clearly not 0.2 because it's much closer to the 0.6 mark, so it's likely 5.7, 5.8, but it's hard for me to say. So that's my estimation there. Some really small measurements, it's really hard to tell that difference between. For example, if we look at this one, we have tick marks here, and it would be pretty hard to really estimate in between because they're so close together. So we have even more uncertainty in that digit. So that brings us to our significant figures and why they're important. And again, when you take lab, you're going to have a more discussion about certainty and measurements and different types of typical chemistry glassware and their different ability to measure. For example, a volumetric glass is a specific volume. If you're following that number where that mark is, let's say you have a 150 milliliter volumetric flask, it's pretty much that mark has been calibrated to where it's 150 milliliters versus a volumetric flask. A graduated cylinder isn't going to be as clear, and like I said, a beaker, you're almost never using a beaker for a measurement. It gives you an idea, a 250 milliliter beaker, but those tick marks are not calibrated very well. And you can see that by measuring out a certain amount of milliliters in your graduated cylinder and then putting it in the beaker, and you'll see it doesn't quite go where it should because we have different certainties. And that's for lab, and you'll learn more about it. Right now, the main purpose I want you to understand is that's why significant figures matter. Because if you're reporting your data to be the most, as a scientist, you want to report what's scientifically and what's observed. And you want to be as clear and truthful with that as possible. So by reporting something in the wrong amount of significant figures, you might be reporting incorrect data by accident if you're not following the significant figures correctly. Because again, it depends on the uncertainty of your measurements. So it's really important we understand that. So we're going to talk about significant figures, talk about our rules for figuring out what figures are significant, and also talking about our calculations with significant figures and what's appropriate. So our non-placeholding digits and a reported measurement are called significant figures. Now we're going to talk about zeros and when they're significant and when they're not. But some zeros are only written to help you locate the decimal point, and we'll discuss those as not being significant. But for example, 12.3 centimeters has 3 significant figures, but remember that last number has uncertainty. So what that says is our measurement is really in a range of 12.2 and 12.4 centimeters, because that last number is understood to be estimated as close as possible. But it does have 3 significant figures. It has 3 non-zero numbers. And again, the more significant figures there are in a measurement, the smaller the range of that value is, because then we're giving less uncertainty to our measurement. But that's really dependent on the instrument we use to make that measurement. So we might have a ruler, and let's say I'm measuring something that's more of an inch, but I'm using a yardstick. It's probably not going to be as sensitive, because it would be much better to use a ruler that's more appropriate for inches or that size measurement. And we're going to learn that throughout when you start doing lab. For example, 12.30 has 4 significant figures, and it ranges from 12.29 to 12.31, so that uncertainty is in these tenths position. So that's a much smaller range than the above range, which is in the hundredths position versus the tenths position. We have a much smaller measurement range. And that's likely from the fact that we used a more sensitive instrument to measure that amount. So let's talk about counting significant figures in our rules. If it's non-zero digits, they're significant. So all non-zero digits are significant, fairly straightforward. And our uncertainty comes in this 1.5. It comes on that 0.5. That's our last number. If we have zeros and it's between non-zero digits, it's also going to be significant. So our zeros between our non-zero numbers are always going to be significant. They're not placeholders, they're important. So 1.05 is 3 significant figures. However, leading zeros, any zeros that come before a whole number or a non-zero number, is going to be insignificant. And to avoid confusion, often scientific notation is used instead. Because in scientific notation, you only include significant figures. So 1, 2, 3, 4, that's our 4 significant figures. So in scientific notation, we have our number that's significant times 10 to whatever number we moved our decimal place. 1, 2, 3. And this is a negative because it's a small number. We had to move our decimal place this way. So oftentimes you see scientific notation used instead of using zeros before. So those zeros before are just placeholders, but they're not significant. However, any zeros in between are, and we're going to talk about the zero and why it's significant in the next point. So this zero is what we call a trailing zero. Trailing zeros may or may not be significant. Trailing zeros are significant if they are after a decimal point. So again, this is a trailing zero. Here's our decimal point, it's after. So then it's significant. However, trailing zeros before a decimal point are only significant if a decimal point is shown. So for example, these two zeros are both significant, but 150 only has 2 significant figures. We don't have that decimal point. That means that this number isn't really known. That's 0. So it's not significant. If you wanted 3 significant figures, the best way to write that one would be to use scientific notation. Because again, in scientific notation, you only show significant figures. You can technically put a 0 here, but don't make the mistake. Typically, this isn't done to make it significant because it's confusing. Because it's not so easy to see that decimal place. And you can't make the mistake of putting the decimal place and putting another 0, because that gives you 4 significant figures. Because, again, zeros after, trailing zeros after a decimal point are significant. That would mean your uncertainty is in this number. But if you could only measure up to this point, that can't be significant. So you can't make something significant if your instrument isn't sensitive enough for it. So the best way, if you did want that zero, that trailing zero to be considered significant, would be to write it in scientific notation with the zero. Because now we have a trailing zero behind a decimal point. And that would be the best way to write it. Those trailing zeros are the most confusing. And it's really important as a scientist to understand not only how to read them, but also how to write them. So again, you're not accidentally reporting incorrect or false data. Because you don't want to report false data. That's very important as a scientist. You want your data to be as accurate and true as possible. So it's really, really important that we draw it correctly. So if we're trying to write that, and we want to write that 150, and we want all three to be significant, writing it in our scientific notation is the best route to do it. So our decimal place is here, and we want to move it 2 places. So our scientific notation would be 1.50 times 10. We moved it 2 places, positive 2. So that would be writing our scientific notation. And then we would have 3 significant figures and we wouldn't have confusion. However, if it's not written that way, if it's just written as 150, then it's only accepted to have 2 significant figures, and our uncertainty is at 5, not that 0. So those trailing zeros are the hardest. Any zeros that are after non-zero numbers. Remember though, if a 0 is between non-zero numbers, it's always significant. If a 0 is after non-zero numbers and it's after a decimal place, then it's significant. If it's not after a decimal place and it's not between non-zero numbers, then it's not significant. And it's really important we report them as it should be reported, either as significant or not. There are also some numbers whose measurements considered exact. So from definitions, we know 1 centimeter is equal to 0.01 meters. That's exact. 1 centimeter is equal to 0.01 meters. So that's considered to have infinite significant figures because it's an exact number. So those that we know with certainty are considered exact numbers. Equations, for example, the radius of a circle equals the diameter of a circle divided by 2. This 2 does not have 1 significant figure. It has infinite significant figures because it's an exact number. So when we are going to be adding and subtracting, we're not going to use that 2 to determine the amount of significant figures because we consider it having infinite significant figures. And we're going to learn that we're going to be looking at the least number of significant figures in some cases. So if it has an infinite number, it's never going to be our least. So we won't use exact definitions or exact numbers in equations to determine the amount of significant figures our final figure after a calculation will have. Because they have unlimited number of significant figures, depending on what we're working with. So let's look at some examples. So in this first example, how many significant figures do we have? So we have 4. We have 3 non-zero numbers. These 2 zeros are coming before our non-zero numbers, so they are not significant. Even though it's after a decimal place, we have to have a non-zero number before, so that after a decimal place only counts for trailing zeros, not zeros that come before any number. So any zeros before a number are not significant. Now this 0 is a trailing 0. It's after a decimal place, and it's after our numbers, so it is significant. So that one has 4. I like to underline them. In the next example, how many significant figures do we have? 5. All those zeros are in between non-zero numbers, so they're all significant. That one's fairly straightforward. In the next one, we have a relationship. How many significant figures do we have? This is one of those examples. That's an exact thing. We know 10 decimeters equals to 1 meter. That is infinite number of significant figures. That will not affect our final significant figure number. And the next example, how many significant figures do we have in these seconds? We have 4. We have trailing zeros that are after the decimal place. Any of these numbers in scientific notation, they're always going to be significant. So 4 significant figures. That's our rule, and that's one of the reasons why we use scientific notation, is because it's an easy way for us to get our point across of which digits are significant. This part is never significant. Only whatever this is. And the next example, how many significant figures? 1. All those other zeros can be 4. And the last example, how many significant figures? Only 1. If we wanted, it's kind of ambiguous, we would say 1. But if, as a reporter, I wanted this to have 3 significant figures, it would be much better to write that in scientific notation. So let's say I wanted it to have 3 significant figures. If my instrument was sensitive enough to measure 3 significant figures and I wanted to report it as such, it would be much better to report this in scientific notation. So I want 3. Here's my decimal place. I'm going to move it 1, 2, 3, 4. But I'm only going to show 2 of those zeros because I only want 3 significant. So this is still going to be 10,000. But I'm only reporting my significant zeros if I wanted to only have 3. So that would be a much more clear way to report that number if I knew that I had 3 significant figures. Well, I only have 1 significant figure, it's perfectly okay to draw it like this. So that's what I mean by it's ambiguous, because it depends on what you want. So scientific notation is a better way when we have a bunch of zeros to report and be clear on what our precision is with our measurement. Some more examples. Again, here, this is a very similar one. We have 1, 2, 3. So this is our point of uncertainty. We have 3 significant figures. This is not the best way to write this one. I put that decimal, so that means it has 3. But really, it should be written as 1.20 times 10 to the 2 to be really clear that it has 2 significant figures. Because it's really, even if you're typing it in, a lot of times Word will get rid of that decimal point. Or some things, and you don't want that if you want this to have the 3 significant. But what this means is our certainty is between these last numbers. This next one we have 4, and as you can see, our certainty. And then this one would be reported the right way to specify 3 significant figures. So now we know where our certainty is. Of course, if you are taking a measurement and we're going to be doing some calculations, you might have to round your final figure to denote the appropriate number of significant figures based on your measurements. So we need to talk a little bit about rounding. But rounding's fairly straightforward, and this is rounding really no different from what you've learned in rounding before. So 0 to 4, we're going to round down. We drop all digits after the least significant figure and leave our least significant figure alone. All insignificant zeros, we might add them to make the value reported correctly. For example, we can put some trailing zeros, or we can show it in scientific notation and not have any insignificant zeros. So depending on how we're showing it. For example, if we need to round 2.34 to 2 significant figures, this number is a 4, so we'll round down and our number will be 2.3. So just pretty much the same type of rounding as before. If our numbers are 5 to 9, we're going to round up, and our last significant figure is going to increase by 1. Again, same thing with rounding. So if we want 2.37 to only have 2 significant figures, then we would, 7 is above 5, so therefore we would round that to 2.4. So really no difference in this rounding than normal rounding. But remember, what we're thinking about is what should we be reporting as significant. As we do calculations with significant figures, to avoid error with rounding, so you don't get a number that's really off, just wait to round at the very end of all of your calculations. Because most of the time it won't make a difference, but if you're rounding at every step, you might end up with your uncertain number being off from what it should be. So what you can do is do all your calculations and then round after you're done. And that's the best way to do these, and as we go through examples, we'll do that. We'll round at the end based on the amount of significant figures we should have. And I'm going to talk about how to determine the amount of significant figures you should have in the next couple of slides. So if we look at 2.34 and we're rounding it to 2 significant figures, then again, that's going to be rounded to 2.3. If we look at this one and we're rounding to 2 significant figures, we're only looking at this 4. Don't try to round each number. Look at that 4. That 4 is under 5, so it's going to come out to 2.3. So you're only, now if we were rounding to 3 significant figures, that would come out to 2.35. So it depends on what amount we're supposed to be rounding to. So don't round that to 2.35 first and then round it after. Just round it based on what it is. And again, it's cases like this where it'll be important to wait to round till the end. So that way you don't get weird numbers and your numbers being slightly off, which means you're reporting false data if you do that. And that might make a difference depending on what you're reporting. If we're looking at this example and we want to round it to 2 significant figures, that can either round to 0.023, or you could write it in scientific notation after you've rounded it. And both of these answers would be appropriate. So pay attention, especially in your homework. Your homework's really specific in how you put things in. And if it asks you for scientific notation, make sure you put that in. If it asks you to put the unit in the abbreviated form, make sure you put it in. So if you were to write milliliters out, it would probably tell you it's wrong, even though everything else you did was right. So be careful with the mastering. It's very specific in what it asks, so read what it's asking you to do. If it's specifically asking you not to put it in scientific notation, this is the way that you're putting it. But in all technicality, both ways to write that are both correct. In this way, you only have 2 significant figures, and the same thing here. So those are both correct. Same thing if we're looking at this one. If we're rounding to 2 significant figures, that would round to 0.024 or 2.4 times 10 to the negative 2. Both cases are fine. And again, if we're looking at this one, and my little arrow is in the wrong place. We're going to be rounding that to 0.023 because 4 is less than 5. So next we're going to talk about applying this to calculations. And remember, I really recommend always having your calculator out in this class. And always having your iClicker out. Because if the time runs down before you get to it, So let's talk about how to determine your calculations depending on if you were actually using those numbers. So first off, understand I'm giving you rules for calculating whether you are adding or subtracting or multiplying and dividing. These rules are based on your uncertainty. So your uncertainty in your actual calculation is only as certain as whatever certainty you had in your measurement. That's what we're trying to come across when we're talking about reporting our data into correct significant figures. So if I have a ruler and I'm only measuring to a certain decimal point with that ruler, I can't report a number past that decimal point of my least certain measurement because I don't know what that number is. My ruler was only up to 0.2. It wasn't up to more than 2 decimal points. So I might have a more sensitive measurement, but when I'm using multiple measurements in a calculation, my calculation is only as good as my least sensitive measurement because I cannot make up numbers that I didn't actually observe. So that's where these rules are coming from. The fact that if I'm measuring something with a certain size ruler, that's as certain as I can be. I can't make up numbers that I didn't actually physically do. Then I'm falsifying data. And that might cause an issue if I'm trying to determine the best concentration of a pharmaceutical to give to someone so they don't die. So it's really important. Sometimes those kinds of problems won't be as drastic as those outcomes. But sometimes they will be, so we always want to make sure that we are reporting correctly and as clearly and truthfully as what our measurements tell us. And if we want a more certain measurement, we want to use a more sensitive instrument. It's as simple as that. Maybe our instrument isn't appropriate for what we're trying to do. So that's where the concept of what I'm going to teach you for our rules comes from. It's not just rules, it's rules based on what we understand with measurements and what we can do. So rules for our significant figures and calculations. With addition and subtraction, our answers should be given in our least number of decimal places in the measured numbers. When we're adding and subtracting centimeters, our final measurement can only have as many decimal places as our number with our least amount of decimal places. Because that is the most uncertain measurement that we've done. Now if we are multiplying and dividing, then we're not going with the number of decimal places, we're going with the least amount of significant figures. And remember, especially with multiplying and dividing, if we are using a calculation that has an exact number, for example, the diameter of a circle, that 2 looked like it only has one significant figure, but it's infinite, so it's never going to be our deciding factor. If we're doing a conversion with known measurements, 1,000 milliliters equals 1 liter, then that 1 for that 1 liter is never going to determine how many significant figures because it's infinite. It has as many significant figures as we need. So that's especially relevant in multiplying and dividing because when we are doing our unit conversions, we're usually multiplying and dividing. So we're going to go through that in more detail. So here we go with addition and subtraction. The result has the same number of decimal places as the measurement with the fewest number of decimal places because our measurement is only as certain as our least certain measurement. So our decimal place can only be as known as the measurement with the least amount of decimal places. So for example, we're adding these 3 numbers. This is our number we come out with. And again, I want to do the rounding at the end once I've done all these additions. So that's all my possible. Looking at our 3 numbers, our 3 measurements, let's pretend like they're in centimeters, but right now we're just using them as examples. This one has 2 decimal places. This one has 3. And this one has 3. So our number with our least is 2. So our final number should be in 2 decimal places. So we're going to round from 9.214 to 9.21. 4 is less than 5, so we drop it and we keep that less uncertain number. So fairly straightforward with addition and subtraction. Here's another example. This one's with subtraction. If I put this in my calculator, 4.8 minus 3.965, I'll get 0.835. Our first number only has 1 decimal place. Our second has 3. That being said, this is a pretty certain number, but this number isn't that certain. So our measurement can only be certain as this one is, and this one's not that certain, it's only certain up to the 10th. So our final answer should only have one decimal place, which is 0.8. So that's for addition and subtraction. We're looking at the amount of decimal places. Now, multiplication and division, we're looking at the least number of significant figures. And both of these, we're looking at the least of something. So here, if I put this in my calculator, I get that big number. But that's not going to be my full number, so I need to look at how many significant figures I have. 5.02, that has 3 significant figures. This one is all numbers, no zeros, so of course I have 5 significant figures. This one's going to be my most precise measurement, my most certain, but my actual measurement can only be as good as my least certain. This one only has 2. This is a leading 0, remember that one's not significant, but we do have a trailing 0 after a non-zero number, after a decimal place, so these 2 are significant. I'm going to underline them so when you're looking back. So that means our final report can only be in 2 significant figures, so that would be 45, or you can put 4.5 times 10 to the 1, but this one's not really necessary because the 0 is not part of the measurement. So that would be our 2 significant figures. Here we're dividing, again that's our number we'd come out with. This first one we have 4 significant figures. Here we have 3. It's a trailing 0, but it's after a decimal place. So our final number should only be reported with 3 significant figures. Oops, sorry. That should be 0.966. You could also write this one in scientific notation if you'd like. But this is perfectly fine. So what if you were adding and subtracting? What do you do if you're doing all of that? So let's look at what we do if we're doing multiple things with a calculation. So when doing different kinds of operations, as far as coming up with the numbers, you learn this in math. We're going to do what's in parentheses first. In this case, we'll do the subtraction. The key here is to evaluate the significant figures. Now remember, don't round until the end. So don't round in this portion. Keep whatever numbers these are, then multiply by these numbers. You're going to get some big numbers, then you round. And the reason why we're going to round at the end is so we don't make a mistake. And in some cases, you won't end up with a different number, but the key here is I should get the correct last uncertain number. So if it should be 5, that's what I want. So if you try to round first and then multiply, you might get a different number for that least certain, and that's not useful. So we want to try to be as clear as possible. So as far as doing the math is the same as you always would. The key is to follow what your significant figure should be. And I'll go through it and explain. So our first step will be what's in parentheses. So what's in parentheses, we have 2 decimal places and 1 decimal place. So that's going to come out to, if I actually take 4.67 and subtract 2.3, I'll get 3.37. What I'm going to do is underline where I should round, but I'm going to keep the 7 for now. So I should be rounding at 1 decimal place because for addition and subtraction, we have the least amount of decimal places. That's what our answer should be in. But I'm going to keep that 7 so I get the correct number. I'm just going to underline it. Then I'm going to multiply by my 3.489. So that's going to come out to this 11.758. Now remember, to determine the correct amount of significant figures, this is 4. That's not changing. There's no difference. Now I know I have the 7 written, but if I had only done this and I had rounded, I would have rounded in this position. So that means now, based on this number, these are my only 2 numbers that are going to contribute to my significance. So that would be 1 decimal place or a total of 2 significant figures. Does everyone understand what I'm saying there? It's really important. That 7's there, but it's irrelevant for our significance. because this fact that this only have one decimal place makes this 7 irrelevant. I'm keeping it so my final numbers are correct, but in my final rounding, I'm going to go by the fact that we're multiplying, and I only have 2 numbers in here that's actually significant. The 7 is not significant. So my final rounding number is going to have 2 significant figures. Why did I put the 1 decimal place? Well, if you were adding here, that would be relevant. But we're not, we're multiplying, so we're going by the least number of significant figures. So I'm just basically writing what's still significant and important in this number. So you wouldn't go by 3 significant figures because that 7 is not significant. But I want to keep that 7 so I don't make a mistake in my final number. Would it have made this 2 different if I had rounded to 3.4? I don't know. It might not. But some cases it will. So just to not make that mistake, so you don't get 13 by accident, you want to just keep all the numbers until the end. In this case, it wouldn't have made too much of a difference if you had rounded before, but sometimes it does, so it's just easy. Instead of always checking, doesn't it make a difference? Just keep the numbers until the end. Oh, sorry, I don't know why. So let's look at some examples for this. Maybe. Okay. So looking at these examples, I don't know what's going on with my eye clicker. And just be patient with the calculations. I don't know. So if we're looking at this first example, we're multiplying and dividing. So in that case, we're going to be going with the least number of significant figures total. So when we're looking at this one, glad I brought my calculator today, so I don't have it written down on my sheet. I usually have everything worked out so I don't have to calculate things in class. So I have the numbers already figured out. I don't know where it is. So because we're doing the division, we can do our division first. So I get 1.15798. I really need a new calculator. I can't see all my numbers. Then we can multiply that number by our other two. I get this number. It's really, really small number. But of course, yeah, okay, so I rechecked my numbers. But our least we're multiplying and dividing. So our answer is going to be based on our least number of significant figures. So we have 1, 2, 3 in this one. We have the trailing 0, but it's after a number and after our decimal place. The next one we have not significant. 1, 2, 3, 4. Which is kind of irrelevant because clearly we have one that's 3, so that's less. Then these are both 5. So our least is going to be our 3. So our final number should have only our 3 significant figures, and whatever that measurement is. If we look at this one and we do this measurement, I have this number. Let me know if this is wrong though, because I can't see all the numbers from a calculator. I need a new one. It has weird little stripes on it. So overall, again, in this case, we're adding and subtracting. So we're going to go by our number of decimal places. So here we have 3 decimal places. Here we have 1. And then here we have 4. So our final number should only have 1 decimal place. So we're going to round, and that's of course going to round to 4.9 because 7 is larger than 5. And we're going to do this one. You're going to work on this one later because I'm going to do the other example with the iClicker question, which is a lot like C. So looking at D, we're going to do what's in parentheses first. So 14.84 times 0.55 is 8.162. Now, I'm going to keep all these numbers, but I'm going to underline what's important, and we're multiplying. So we have 2 significant figures here, and then here we have 4. So we're multiplying, so we're going with the number of significant figures. So we only have 2 that we can report. And the book will only underline the most uncertain, but when I'm doing this, I like to underline all my significant figures, just to be clear with myself. So I know I have 2 significant figures there. Then we're subtracting. So that number equals 0.142. But we only have 1 decimal place that is significant in this example. So here we have 2. So we only want 1. So we're going to round that to 0.1. And then, like I said, I'm going to go over the iClicker one in the next slide. So I'm just going to skip C because of time. So looking at this iClicker question, again, we're just going to be going through our math here. And actually, what I'm going to do if I have room to do it. Okay, so what we're looking at here is we're going to do what's in parentheses first. We can start with our subtraction on our top number. Or we can start with the second portion. So it doesn't really matter. I'm going to start with over here. So if I work out what's in my parentheses, 2.83 times 0.360. I'm going to get these numbers. And again, I want to keep all these numbers so I don't make a mistake later on. But we're multiplying, so this has 3 significant figures. And this one also has my 3 significant figures. So looking at this number, here are my figures that are significant, because it should have 3. So I'm just going to underline them. The next thing I'm going to do is those other parentheses, the subtraction in the next portion. So when I subtract my 1.428 minus 1.08, I'm going to get 0.348. So here we're subtracting. So now I'm looking at my decimal places. We have 3 decimal places here. And this one we only have 2. So in my number, what's important is my 3-4. So that's 2 decimals, and that's actually 2 significant figures as well. Again, I'm not going to round yet. Next thing I'm going to do is divide. So when I divide my 0.348 divided by 0.288, I get my 1.2083. This number only has 2 significant figures. This one has 3. We're dividing, so this number should only have 2 significant figures. I'm going to underline them. So that's 1 decimal place, and then my other one, notice, has 2 decimal places. So when I add up those 2 numbers, whatever those numbers come out to be, it's 1.0188. So we're adding, so we're going with the least number of decimal places, which is 1. So when I round that, oh, sorry. I just rewrote 1.88. When I round it, it's going to come out to 2.2. And that's my 1 decimal place. So that's how you follow them when you have multiple things you have to go through. And I really recommend underlining or highlighting or using a colored pencil for following these. Y'all have a good day. Oh, I'm going to restart the iClicker in case you still haven't gotten it.
Because soccer.
Yeah.